Dear students, today we are going to start electric field due to point charge and due to electric dipole. First, let us see the electric field definition. Electric field is defined like this. It is the space or region around a charged body in which if any other charge is placed, it experiences an electrostatic force. That means, let us suppose that we are having a charge Q placed at this place. Then the region around this charge or the space around this charge in which if I will place any other charge, say Q0, then this charge will experience electrostatic force. Then we call the space or region around this charge as the electric field. This charge is also called source charge. Now, when I will place the charge Q0 in the electric field created by the source charge, then it will experience the electrostatic force. That means the space around the source charge in which if any other charge is placed will experience the electrostatic force, then that space or region is called the electric field of the source charge. The electric force experienced by the charge Q0 is a two-step process. In step first, this source charge produces something called electric field in the space around it. That means step first is creation of the electric field by the source charge. In the second step, when you are placing any other charge in it, then it will experience the force. The Q0 charge will experience the force when placed in that electric field. It indicates that first there is a creation of electric field, then when any other charge is placed in that electric field, it will experience the force. Therefore, electrostatic force is a two-step process. First, electric field is created, then when placed this charge in that electric field, it experiences the electrostatic force. This electric field has its own existence. That means it does not depend on any other thing. It has its own existence. It is present, this electric field created by the source charge is present even if there is no any other charge placed in this field. That means this charge Q0 only indicates the field. Only indicates the field whether there is field at this point or not. Whereas the electric field is present when this Q0 is here or when this Q0 is not here. Second thing regarding the electric field is it takes finite time to get get propagated. That means if we are interested to know the electric field at this point P, when the source charge is at the point O, let us suppose that the electric field at point P is X. If I am going to move this source charge from Q to some other point, then field at X will get changed. The time taken by the field to get changed at X is given by R divided by C, where R is the distance moved by the source charge and C is the velocity of light. In other words, we can say the electric field propagates with the velocity of light. Now, there is another term called electric field intensity. Electric field intensity is the measure of electric field intensity is the measure of electric field at any point within the field. For example, if we are interested to know the value of electric field now at a point P, which is at a distance R from the source charge Q, if we are interested to find the electric field at point P, value of electric field at point P due to the source charge Q, which is at a distance R, then that value of electric field at point P is called electric field intensity and is defined as the force experienced by the unit positive point charge. Unit positive point charge. It is represented by the symbol Q naught and is sometimes also called test charge. Now, in order to know the electric field intensity at point P, I told you it is the force experienced by unit positive point charge when placed at point P due to the source charge. For example, let us place a unit positive point charge Q naught at point P, then find the force experienced by Q naught due to the source charge Q. Let us suppose that the force experienced by Q naught, force due to Q on Q naught, is represented by F. Then electric field intensity represented by E is equal to force experienced by the test charge divided by the test charge. The electric field intensity is a vector quantity. That means it has both magnitude as well as direction. Therefore, in vector form, electric field intensity is equal to force in the vector form divided by Q naught. The magnitude of electric field intensity is the magnitude of force divided by Q naught, and its direction is same as that of the force experienced by unit positive point charge when placed in the field. In order to know the direction again, let us suppose that source charge which we have considered already is positive, and this test charge is also positive. As I told you, it is unit positive point charge. Then force experienced by Q naught due to Q acts in this direction because there will be repulsion between the two. So this is the direction of force. Therefore, direction of electric field at point P is same as that of the force. If the source charge is negative and we are interested to find electric field intensity at P, place a test charge Q naught at P, then force experienced by Q naught due to the negative source charge acts towards the negative source charge, with the result force direction is like this, and same is the direction of electric field intensity. Thus, magnitude of electric field intensity is F by Q naught, and its direction is same as that of the force experienced by the unit positive point charge when placed at that point. Now this is about the electric field. Now let us derive the first expression for electric field due to point charge. Electric field intensity due to point charge. Suppose we are having a point charge of value Q, place it at point O, and we are interested to find the value of electric field intensity at point P, distance R from Q. In order to know the value of electric field intensity, we have to place a unit positive test charge at point P. Then in the first step, we have to calculate the force experienced by unit positive test charge by using Coulomb's law. Let F be the force experienced by unit positive point charge at P due to the source charge at O. Then F by Coulomb's law will be equal to Q naught by 4 pi epsilon naught R square, as we have studied this thing from Coulomb's law. Call this as equation first. Now, by the definition of electric field intensity, the electric field intensity at point P is the force experienced by the test charge divided by the test charge. Let us substitute the value of force from equation first in this expression. Then we get Q, instead of F I have to write this expression, Q naught by 4 pi epsilon naught R square whole divided by Q naught. Here Q naught and Q naught will get cancelled. That is, electric field intensity at P will be equal to Q, that is source charge, divided by 4 pi epsilon naught R square. This is the expression for electric field intensity at point P, distance R from the point charge Q. The units of electric field intensity from its definition, force per unit charge force is measured in newtons and charge in coulombs, therefore units are Newton per coulomb. So this is the expression for electric field intensity due to point charge at distance R from the point charge. Now we will derive the expression for electric field intensity due to electric dipole. First, in order to derive the expression for electric field intensity due to electric dipole, we must know what is the electric dipole and what is its electric dipole moment. First, I will write here electric dipole. In physics, we are defining the electric dipole as when two equal and opposite charges are separated by some small distance, then it constitutes an electric dipole. For example, let us suppose that I am having two charges, positive charge Q and equal amount of negative charge Q, which are separated by some distance, say 2a. I will call here the distance between the two charges as 2a. This dotted line which I drawn here is the line joining the centers of the two charges. Let us suppose that this is the center of this line. From the center, call this point as C. This as, let us suppose that Q, positive charge Q is placed at A and negative charge Q is placed at B. Then here from C, from the center of the two charges to B, the distance is A. From the center to A, the distance is A. That means from positive charge to negative charge, the distance we consider here is 2A. That is why I took the distance between the two charges 2A. From the center of the two charges to one of the charges is A. From the center to another charge is A. That means distance between the two charges is 2A. Now, when this distance between the two charges is very small as compared to the distance where we are interested to find the electric field, then this arrangement is called an electric dipole. That means, let us suppose that due to these two charges, we are interested to find electric field at point P. Where P is, let us suppose that it is at a distance R from the center of the dipole. This C is called the center of the dipole now. From the center of dipole, if we are interested to find electric field intensity at P, which is at a distance R, now if R is much greater than the distance between the two charges, if R is greater than the distance between the two charges, then this arrangement of the two equal and opposite charges separated by a distance 2a is called an electric dipole. Now, we have to find the electric field intensity due to this electric dipole. If we are going to define what the electric dipole is, we can say it is when two equal and opposite charges are separated by some small distance. In order to get the expression for electric field intensity, another term regarding the electric dipole which we must know is called electric dipole moment. Electric dipole moment, let us consider first of all the electric dipole consisting of two equal and opposite charges separated by a distance 2a. In order to define the electric dipole moment represented by the small letter p, it is also a vector quantity having magnitude as well as direction. This dipole moment P has a magnitude equal to either charge multiplied by the distance between the two charges. That means either charge means one of the charges out of the two into the distance between the two charges. Thus, magnitude of electric dipole moment is Q into 2A, and then units are coulomb meter. Q has a unit coulomb and distance has a unit meter, so the units of dipole moment are coulomb meter. This is the magnitude. Now, what is the direction of this electric dipole moment? It is always from negative charge towards the positive charge. The direction of electric dipole moment is from negative to positive charge in an electric dipole. Whereas in chemistry subject, we are showing the direction of electric dipole moment from positive to negative, but in physics we have to take it from negative to positive charge. Let us derive the expression for electric field intensity now due to electric dipole. In order to derive the expression for electric field intensity due to electric dipole, we consider here two cases. Case first, and then we will consider the case second. In case first, we will derive the expression for electric field intensity due to electric dipole on a line called axial line of the electric dipole. At any point on a line called axial line of the electric dipole. Now, what is axial line of the electric dipole? Axial line of electric dipole is the line joining the centers of the two charges. That means if I will draw a line which passes through the centers of the two charges and produce it on the both sides, then this line is called the axial line of electric dipole. This which I draw here, Q minus Q, distance between them 2A. Let this be point A where the positive charge is placed, this is point B where the negative charge is placed, and let us suppose that this is the center of the electric dipole C. Now, we are interested to find electric field intensity due to electric dipole at any point on this axial line, but except between the two charges. Except between the two charges means this region, plus Q and minus Q के बीच में, between plus Q and minus Q, we have to not consider any point, we have to consider point either away from B or away from A. Let us take the point here, P, where we are interested to find electric field intensity due to this whole electric dipole. In order to do that, first let us suppose that the point P is at a distance r from the center of the electric dipole, that is from C. Let P be at a distance r from the center of the electric dipole where we are interested to find electric field intensity. Now, in order to derive the electric field intensity expression at P on the axial line of electric dipole at a distance r from the center of the electric dipole, we have to use superposition principle. As already you know, the superposition principle states that in order to get the electric field at point P, first consider the one charge out of the two, find the electric field due to this charge at P, then find the electric field due to this charge and P both in magnitude and direction. Then take the vector sum of these two electric fields at point P, we will get the resultant electric field. This is what is called superposition principle. We have to apply the same in order to get the electric field at point P due to electric dipole. Let us consider first of all charge plus Q at A. Let E1 be the electric field at P due to charge plus Q at A. E1 will represent the electric field intensity at P due to charge plus Q at A. Then the value of E1 electric field intensity at P due to the charge at A is equal to, we have to use the same expression as we have done earlier, electric field due to point charge at point P, which is equal to, how much is the point charge here? Q divided by 4 pi epsilon naught. How much is the distance between the point charge and the point P? The distance between these two is, center to P is R, center to A is A, small a, then between the two it is this A, and from C to P R, that means it is R plus A. So here we have to use the same this value, R plus A square. Let us call this as equation first. Now let us see the direction of this electric field at point P. Since this is a positive charge, and if we place a test charge Q0 at point P, it will experience a force whose direction is outwards. Therefore, electric field at point P due to the charge plus Q at A has a direction outwards like this. So this is the direction of electric field at point P, whose value is given by equation first. In the same way, let E2 be the electric field intensity at P due to charge at point, due to charge minus Q at point B. Then E2 will be equal to Q in magnitude. E2 is equal to Q by 4 pi epsilon naught, distance between this charge minus Q and point P. Since from the center to P it is R, and from center to B it is A, then from center to P it is R minus this distance, that means from B to P it is R minus A distance. So I will write here R minus A square. Call this as equation second. Let us find this direction. Direction of E2 at point P. At point P, electric field due to negative charge. If I will place a test charge at point this, the negative charge will attract the test charge. Force will be acting on this direction. Therefore, electric field has the same direction as that of the force experienced by the unit positive point charge. So, electric field direction at point P due to charge minus Q will be towards the charge minus Q. Now, from the diagram, we have seen the two electric fields are acting in the opposite directions. Therefore, from the vector algebra, net electric field E at P will be equal to the difference between these two electric fields, that is, difference between E1 and E2. Since negative charge is closer to point P than the positive charge, therefore E2 will be more than the value E1. So if we take the difference in magnitude, it is E2 minus E1. Or I will write E equal to net electric field at P due to dipole will be equal to E2 minus E1. E2 from equation Q by 4 pi epsilon naught R minus A whole square minus Q E1 value from equation second will be equal to 4 pi epsilon naught R plus A whole square. So this is the expression which we have to solve in order to get the net electric field at point P due to the electric dipole. From this expression we see Q 4 pi epsilon naught, Q 4 pi epsilon naught are the similar terms. We will take them common. That is E is equal to Q by 4 pi epsilon naught into what remains inside the bracket is 1 by R minus A whole square minus 1 by R plus A whole square. Let us solve it. It is E equal to Q by 4 pi epsilon naught. Let us cross multiply it. It is R plus A whole square minus R minus A whole square whole divided by R minus A whole square into R plus A whole square. I will write it like this: Q by 4 pi epsilon naught. Let us solve this. It is R plus A whole square is R square plus A square plus 2AR minus, solve this, it is R square minus R square plus A square minus 2AR divided by, let us write it, R minus A into R plus A whole square, or E equal to Q by 4 pi epsilon naught into R square, and this minus R square will get cancelled when we multiply with minus sign here. R square will get cancelled, A square will get cancelled. It is 2AR minus, and this minus will be plus 2AR, it becomes 4AR by, this is A minus B into A plus B formula, so I will write it R square minus A square whole square, or I can say it is E equal to Q by 4 pi epsilon naught into, here 4AR, instead of 4AR I will write 2A into 2R divided by R square minus A square whole square, because when you multiply the two it will get this, we will get the same value, or E is equal to, the expression will be written like this: Q into 2A into 2R by R square minus A square whole square R. E is equal to Q into 2A, as already I told you, the electric dipole moment P has a magnitude equal to product of either charge into distance between the charges in case of an electric dipole. Then instead of this term Q into 2A, I will write P, that is electric dipole moment, into 2R divided by R square minus A square whole square. This is the expression for electric field intensity at point P due to electric dipole. Now, in this expression, here the term 4 pi epsilon naught is also here. E equal to P into 2R by 4 pi epsilon naught R square minus A square. Now, in this expression, as I told you in the earlier, in the beginning of the class, that the distance between the two charges is much smaller than the distance where we are interested to find the electric field intensity. That is, here R is much greater than A, from this condition, if we will look to this expression here, it is A square. When R is much greater than A, then A square as compared to R square can be neglected. Then we can say E will be equal to P into 2R by 4 pi epsilon naught. A square can be neglected in comparison to R square because R is much greater than A. So it remains here R raised to power 2 whole raised to power 2, that is R4. Or I can say E is equal to 1R, and out of the 4, 1 will get cancelled, it remains 3. That means the final expression will be P into 2R. I will write it as 2P divided by 4 pi epsilon naught R raised to power 4. Out of that, 1 will get cancelled, it remains R raised to power 3. So this is the final expression for electric field at point P. That means electric field due to the dipole at any point on its axial line, at any point P on its axial line, distance R from the center of the dipole is given by 2P by 4 pi epsilon naught R cube. Now let us see the direction of this electric field at point P. Here E2 is in this direction and E1 has a direction like this. As we know, negative charge is much closer than the positive charge, therefore E2 electric field is greater than E1 electric field. So the net field at point P has a direction like this towards the center, but we know already the direction of electric dipole moment is from negative charge to the positive charge. This is the direction of electric dipole moment. This is the direction of net electric field at point P. The two directions are same, therefore we can write in vector form as electric field is equal to twice electric dipole moment in the vector form 4 pi epsilon naught R cube. It indicates that electric field at point P due to electric dipole has same direction as that of the electric dipole moment. So this is the final expression for electric field at any point on the axial line due to electric dipole. Thank you.